The brain works like a resonance chamber. The brain works like a resonance chamber. You're listening to Technical News Reading, presented by Hakeem Alibokis Alexander on Spreaker. Social podcasting, presented for World Reading Club in association with Uniquilibrium. This edition's reading focus comes to us from neurosciencenews.com. It was published on February 6, 2023, and is titled, "The Brain Works Like a Resonance Chamber." Summary. Using advanced neuroimaging techniques, researchers discovered distant brain regions oscillate together in time. Source: Champalimaud Center for the Unknown. It's been over 20 years since neuroimaging studies using functional magnetic resonance imaging, fMRI, a widely used technology to capture live videos of brain activity, have been detecting brain-wide complex patterns of correlated brain activity that appear disrupted in a wide range of neurological and psychiatric disorders. These patterns form spontaneously, even at rest when no particular task is being performed, and have been detected not only in humans, but also across animals, including monkeys and rodents. Although such spatial patterns of correlated activation have been consistently detected across neuroimaging centers around the world, the nature of these correlations was not clear. We do not yet fully understand how the brain communicates over long distances. We know that distant areas exhibit signal correlations and that they are implicated in brain function, but we do not completely understand their nature, says Noam Shemesh, principal investigator of the preclinical MRI lab at the Champalimaud Foundation in Lisbon and senior author of a study published today in the journal Nature Communications. In this study, we wanted to understand what lies underneath those correlations and investigate the mechanisms involved, stresses Shemesh. A number of theoretical works had proposed that these patterns could be explained by standing waves, whose peaks and troughs do not move in space, resonating in the brain structure, that is, by waves analogous to the modes of vibration in musical instruments. But there was little experimental evidence to support this hypothesis due to the poor temporal resolution of fMRI, reaching only an image or two per second. If we could find that the spatial patterns oscillate, this would provide evidence supporting the resonance hypothesis, says Joanna Cabral, first author of the study, from the Life and Health Sciences Research Institute of the University of Minho, and a visiting scientist in Shemesh's lab since 2019. So what the team did was to speed up image acquisition, and they discovered that the signals in distant brain regions actually oscillate together in time. These oscillatory patterns look like a higher dimensional analog of resonance modes in musical instruments. They are akin to reverberations, to echoes inside the brain, says Cabral. Our data show that the complex spatial patterns are a result of transiently and independently oscillating underlying modes, just like individual instruments participate in creating a more complex piece in an orchestra, says Shemesh. The distinct modes, each contributing something to the overall picture at different timescales and different wavelengths, can be added up together, generating complex macroscopic patterns similar to the ones observed experimentally. To our knowledge, this is the first time that brain activity captured with fMRI is reconstructed as the superposition of standing waves, he points out. The new study thus strongly points to a key role for these resonant waves, or modes, in brain function. These resonant phenomena, the authors believe, are at the root of the coherent, coordinated brain activity that is needed for normal brain function as a whole. Ultra-fast MRI. The researchers detected the resonant modes in rats in the resting state, which means the animals were not subjected to any specific external stimulus. Indeed, no tasks were needed, for, as already mentioned, even when we, and mammals in general, are doing nothing in particular, our brains continue to generate spontaneous activity patterns that can be captured by fMRI. To visualize the oscillations, the researchers created videos of activity using the potent ultra-high field experimental MRI scanner in Shemesh's lab and performed ultra-fast experiments developed some time ago by that lab for other purposes. Noam and I met in 2019 and we decided to obtain recordings of brain activity at the maximum temporal resolution we could achieve in the 9.4 Tesla scanner at his lab, recalls Cabral. Noam designed the experiments, Francisca Fernandez performed them, and I did the data analysis and the visualization. Noam managed to achieve a temporal resolution of 26 images per second and thus obtained 16,000 images per 10-minute scan instead of 600 images at the typical resolution of 1 image per second. Like waves in the ocean. When we first saw the videos of the recorded brain activity, we saw clear waves of activity, like waves in the ocean, propagating in complex pattern within the cortex and the striatum, says Cabral. And we found that the signals could be described by the superposition of a small number of macroscopic stationary waves, or resonant modes, oscillating in time. Notably, each standing wave was found to cover extended areas of the brain with peaks distributed in distinct cortical and subcortical structures, forming functional networks. The researchers experimented with rats in 3 different conditions: sedated, slightly anesthetized, and deeply anesthetized. In fact, the animals were lightly sedated in the resting state to avoid any discomfort to them. The spatial configuration of these stationary waves was very consistent across rats scanned in the same condition, Cabral points out. Shemesh adds, "We showed that brain functional networks are driven by resonance phenomena. This explains the correlations that are otherwise observed when you do slow imaging. Long-range brain interactions are governed by a flow of information that is oscillatory and repetitive." Pathological states. They also found that increasing the amount of anesthetic reduces the number, frequency, and duration of the resonant stationary waves. As already mentioned, previous studies have shown that certain patterns of brain activation are consistently altered in disorders of consciousness. So this experimental design, says Cabral, was actually also meant to mimic different pathological states. Our featured image shows a scan here, probably using their fMRI, and the caption reads, "Signals captured with fMRI from a rat brain viewed on top of an anatomical image of the animal. Contralateral areas colored in red activate together at the same time, despite the long distance between them." Credit Joanna Cabral. Functional networks appear disrupted in several neurological and psychiatric disorders, she points out. If confirmed in humans, she speculates their results could also lead to the use of resonant modes as biomarkers for disease. Our study also provides a new lead in looking at disease, corroborates Shemesh. We know that long-range brain activity is strongly impacted in disease, but we do not understand why or how. Understanding the mechanism of long-range interactions could lead to a completely new way of characterizing disease and hinting on the type of treatment that may be necessary. For example, if a specific resonant mode was missing from a patient, we might want to find ways to stimulate that particular mode. More work will obviously be needed to confirm To confirm all these results, the researchers agree, and whether they are replicable in humans. But once we understand better the nature of functional networks, we can design informed strategies to modulate these network patterns, says Cabral. This is precisely the subject of the researchers' new project, BrainStim, predicting stimulation strategies to modulate interactions between brain areas. Funded by the La Caixa Foundation and the Portuguese bank BPI with 300,000 euros, it is a collaboration between the Life and Health Science Institute of the University of Minho and the Champalimaud Foundation, and its aim is to better understand the impact of distinct pharmacological and electromagnetic brain stimulations in the modulation of these macroscale oscillatory modes. About this neuroscience research news. Author Anna Gershenfeld. Source Champalimaud Center for the Unknown. The image I referred to earlier is in the public domain. The original research is under open access and is titled Intrinsic Macroscale Oscillatory Modes Driving Long-Range Functional Connectivity in Female Rat Brains Detected by Ultrafast fMRI by Noam Shemesh and others in Nature Communications. You've been listening to Technical News Reading presented by Hakeem Ali Bokus Alexander on Spreaker. Social podcasting presented for World Reading Club in association with Uniquilibrium. This edition's reading focus comes to us from neurosciencenews.com, which now returns with an abstract from the paper titled Intrinsic Macroscale Oscillatory Modes Driving Long-Range Functional Connectivity in Female Rat Brains Detected by Ultrafast fMRI. Spontaneous fluctuations in functional magnetic resonance imaging fMRI signals correlate across distant brain areas, shaping functionally relevant intrinsic networks. However, the generative mechanism of fMRI signal correlations, and in particular the link with locally detected ultra-slow oscillations, are not fully understood. To investigate this link, we record ultra-fast, ultra-high field fMRI signals, 9.4 Tesla, temporal resolution equals 38 milliseconds, from female rats across 3 anesthesia conditions. Power at frequencies extending up to 0.3 Hz is detected consistently across rat brains and is modulated by anesthesia level. Principal component analysis reveals a repertoire of modes in which transient oscillations organize with fixed phase relationships across distinct cortical and subcortical structures. Oscillatory modes are found to vary between conditions, resonating at faster frequencies under methamphetamine. Alright, so oscillatory modes are found to vary between conditions, resonating at faster frequencies under methamphetamine sedation and reducing both in number, frequency, and duration with the addition of isoflurane, peaking in power with clear anatomical boundaries. These oscillatory modes point to an emergent systemic property. This work provides additional insight into the origin of oscillations detected in fMRI and the organizing principles underpinning spontaneous long-range functional connectivity. You've been listening to Technical News Reading, presented by Hakeem Ali Bokus Alexander on Spreaker. Social podcasting, presented for World Reading Club in association with Uniquilibrium. This edition's reading focus comes to us from neurosciencenews.com. It was published on February 6, 2023, and is titled, The Brain Works Like a Resonance Chamber. You can read this article and others like it for yourself by visiting neurosciencenews.com. That's neuroscience.com. neurosciencenews.com. The brain works like a resonance chamber.